once again in honor of Jack, who has been inspiring to all of us. And tonight we have a joint talk by Sarah Koch and Eriko Hironaka. And they're going to talk about the disconnected deformation space of rational maps.
Okay, well, thank you very much for coming. Thank you, Julio, for introducing us. Thanks very much to the organizers for giving me a chance to speak here. Thanks, Jack, for having an 85th birthday conference. And I just want to say, I remember 5 years ago at Jack's 80th birthday conference in Banff. I was speaking with Tan Lei and Bill Thurston. And Bill Thurston told us that he had this idea that the shape of rational maps was something that had yet to be revealed. There was a picture of rational maps that we still didn't know, or we still didn't have. That was a very inspiring comment. And I have no idea where this project fits in the context of that remark, but I would have loved to have shared this work with both of them, and I wish they were here. Okay, so this is a project that I'm working on with Koch y Eriko. This talk will be delivered to you in 2 pieces. I will tell you the first part, exactly what the problem is. I will reduce the problem down to a specific concrete topological problem, and then Eriko will come in and talk about how to solve that particular topological problem. So we are going to be interested in the topology of a certain deformation space. And a lot of the ingredients that one uses to define this deformation space have already been in the air at this conference in at least 2 different presentations. There's Nikita Selinger's mini course on Thurston's topological characterization of rational maps, and there's Jan Healy's talk about the curves Sn in the critically marked cubic polynomial moduli space. So some of these ingredients you will see again in this presentation as well. So Eriko and I are interested in the topology of a deformation space that was defined by Adam Epstein in his PhD thesis in 1993. Okay, so I'll first define all of the preliminary objects that we need in order to tell you what that deformation space is. I'll present our theorem and then talk a little bit about the setup of the problem at hand before I pass it off to Eriko to tell you how to do sort of the topological part, the topological computation. Okay, so we're going to work topologically. Here are our preliminaries. S2 for us will be an oriented topological 2-sphere. When I use the notation A and B, these will always be finite subsets of the topological 2-sphere that contain at least 3 points each. This is a lasting convention, a standing convention for this talk. And by this notation, here, when I have a map between a pair, a space and a finite set, and a space and a finite set, I mean that that's a map of pairs, meaning that it maps this space on the left to this space here, and it maps this set, which will be finite for us, to this finite set down here. Okay, so those are our conventions for this talk. We're going to need a Teichmuller space for what I'm going to define for you. You've seen this in Nikita's mini course. Let me just run through the definition again. This is the Teichmuller space with respect to the finite set A on the sphere S2, and its definition is the set of classes of orientation-preserving homeomorphisms from the topological 2-sphere to the Riemann sphere up to equivalence. The equivalence is that two of these homeomorphisms are the same or equivalent if there's a Mobius transformation mu so that the first homeomorphism is equal to the second followed by that Mobius transformation on the finite set A. And the second part is an isotopy condition, namely that phi1 is isotopic to the second homeomorphism phi2 followed by that same Mobius transformation relative to the set A. The Teichmuller space is a complex manifold. Its complex dimension is the size of A minus 3. All right, so we have 2 subsets of the topological 2-sphere. And again, remember A and B, they're finite. They both contain at least 3 points. That automatically gives us 2 Teichmuller spaces. And there they are. Now I'm going to impose some conditions on A and B and perhaps introduce some other ingredients to manufacture maps from TB to TA. First, if A is a subset of B, then there is a map called sigma sub AB from this Teichmuller space to this Teichmuller space, which I'll call the forgetful map. I'll define this for you precisely on the next slide, but essentially it maps the class of a homeomorphism phi in this Teichmuller space, where the equivalence is rel B, to the class of that same homeomorphism in this Teichmuller space, where the equivalence is rel A. This makes sense because A is contained in B. Okay, so this is called the forgetful map. Now I'm going to erase this assumption, get rid of it completely, and start with a different set of assumptions in red. Now I have an orientation-preserving branched cover mapping this topological two-sphere with this finite set to this topological two-sphere with this finite set marked. The only other condition that I am assuming is that B contains the critical values of the map F. Under that condition, you get a map from this Teichmuller space to this Teichmuller space, which I'll denote as sigma F, and this is called the pullback map that comes from pulling back complex structures. I'll define it precisely for you on the next slide, but this map showed up in Nikita's mini course, I'm sure. So the point is that when we have all of our conditions, the blue condition and the red condition, we have two maps from this Teichmuller space to this Teichmuller space. And when Adam talks about his deformation space, he likes to say, whenever you have two maps between two spaces, that's also dynamics. So I'll just throw that out there as another quote. So one thing that you could do in this particular context is define what he calls the deformation space of F. There are 3 data points for this object. There's this map and these two finite sets satisfying those conditions. By definition, this is the equalizer of the two maps from type B to type A. Okay, so it's the set of points in the domain Teichmuller space where the maps agree. I'll talk about why this is a natural object to study on the next slide, but I would like to emphasize that this object may be empty. All right, so as I said before, this is sort of just adding some details to those definitions. The forgetful map will map the class of the homeomorphism phi inside this Teichmuller space to the class of that same homeomorphism, but in this Teichmuller space. Okay, so that's our forgetful map. That map is a holomorphic surjective submersion. And here's the definition of the pullback map. Now, in this definition, I would like to emphasize that unlike this definition, which requires some relationship between A and B, namely containment, that this definition, the definition of this sigma F, is completely non-dynamical in the sense that the domain here is not identified at all with the range here. There is no relationship between A and B other than the fact that F maps A to B. Okay. So this is a non-dynamical definition of pullback. So how is it defined? Again, this is probably presented a lot in Nikita's mini course. We start with our branched cover over here. We take a homeomorphism over here to the Riemann sphere, where this homeomorphism maps this finite set over here to this finite set of marked points on P1. This homeomorphism here induces a complex structure up here just coming from pullback. This map is a local homeomorphism at all but finitely many points. There's a homeomorphism psi up here and a rational function capital F so that this diagram commutes. And the pullback map will map this class of the homeomorphism, the class of the homeomorphism phi, to the class of the homeomorphism psi. Okay, so this I hope is familiar to a lot of you so far in this conference. Okay, so this map is holomorphic. All right, so let's talk about what exactly it might mean to be inside the equalizer, to be a point in this deformation space. Why this might be a natural thing to study. All right, so we have our two Teichmuller spaces, we have our red map and our blue map on Teichmuller spaces. Here are the conditions, the red condition and the blue condition, that guarantee that you have these two maps. And remember, this def space is their equalizer, which again might be empty. Over here, this is basically the commutative diagram from the previous slide. Okay, so this is the diagram that defines the map sigma F. A homeomorphism down here, we pull it back, get a homeomorphism here, and a rational function, so this diagram commutes. The homeomorphism that you get up here is not unique. Okay? It's unique up to post-composition with a Mobius transformation. So even if F has some interesting dynamics, so over here you should think of this side, there's an identification limitation or a containment relation between A and B. So we're identifying domain and range of little f over here. You take an arbitrary element of Teichmuller space, a homeomorphism, you pull it back, you get a rational function. There isn't necessarily any relationship between this marked set up here on this Riemann sphere and this marked set of points down here on this Riemann sphere. So for example, if A, say, contains a cycle of period 3 for the map little f, take any element of Teichmuller space and pull it back, you get a rational function over here so that the diagram commutes, but this set of points might be totally different from this set of points. So what does it mean if the homeomorphism phi belongs to the deformation space? It means that you can find a homeomorphism psi which agrees with the homeomorphism phi on the set A. A lives up here and it's a subset of B. What this is saying, this first pink point up here, says that this diagram commutes and that the combinatorics of f restricted to A over here agrees with the combinatorics of capital F, this rational function, restricted to this finite set of points over here. So the dynamical object, like maybe there's some periodic cycles in the set A, periodic cycle in period 85 or period 70. So if you find a point in the deformation space, A contains those periodic cycles, you pull it back, you get this homeomorphism up here, then this rational function will have a periodic cycle of period 85, a periodic cycle of period 70 inside this marked set of points. Also, we know that this homeomorphism will be isotopic to this homeomorphism relative to the set A. This is exactly what it means for the homeomorphism phi to represent an element of the deformation space. It's the equalizer of these two maps. And if you look at this carefully enough, you'll notice that really what this is saying is that the homeomorphisms phi and psi give you a combinatorial equivalence between your topological branched cover, this pointer is a little bit tired, between your topological branched cover and this rational map over here. So you can think of the following statement. The deformation space is non-empty if and only if your topological map is combinatorially equivalent, where that notion is relative to A, is combinatorially equivalent to a rational map. And that sounds an awful lot like the statement of Thurston's theorem. Speaking of which, so in the purely dynamical setting, where the sets A and B are equal, Thurston's topological characterization could be restated as follows. The deformation space, which in the purely dynamical setting would be the set of fixed points of the pullback map, sigma f. The deformation space is non-empty if and only if that branched cover admits no obstructing multicurves. And another consequence of Bill's theorem is that the deformation space in this purely dynamical setting where the sets A and B are equal, the deformation space is always connected. Maybe empty, but it's always connected. So these are two topological results in the purely dynamical setting. And one might ask, what are the analogs of these results in the setting where A is only a proper subset of B? What is a criterion for which the deformation space is non-empty? Is the deformation space always connected? So these are the kinds of questions we're interested in. Just one more thing about the structure of this space. If you start not with a branched cover, but with an actual rational map, the deformation space is automatically non-empty because it contains the element in Teichmuller space corresponding to the identity map, P1. So Adam has a theorem which says that if we start with a rational function f, satisfying those properties from the previous slides about A and B, B containing the critical values, A maps to B, subset of B, we can study its deformation space. Let's suppose that it's not a Lattes map. His theorem is that the deformation space is a smooth, complex analytic submanifold of this Teichmuller space, and its dimension is the difference, it's the size of the difference between the sets A and B. So this is a local result. It doesn't tell us anything about the global topology. Okay, so Echo and I proved that the deformation space is not always connected. So I'll tell you what our example looks like and set up the problem and then pass it over to her. So our result involves the following class of maps. So Jack has this beautiful paper on the geometry and dynamics of quadratic rational functions. And in that paper, he defines the locus pier 4, 0, which is exactly the analog of a space we saw earlier today, but in cubic polynomials. So pier 4, 0 in the Modulite space of quadratic rational maps consists of conjugacy classes of quadratic rational maps that have a critical point that's periodic of period 4. Okay, that's an algebraic curve inside this two-dimensional Modulite space. So an element of pier 4, 0, we can choose coordinates and represent it with a rational function that has a critical point at 0, corresponding critical value at infinity. Infinity maps to 1 maps to something called A, and then A maps back to 0. And the other critical point of the rational map is here. The critical value is something I'll call B. Okay? So I'm setting up a deformation space problem for a map inside pier 4, 0. So I want to mark the 4 points in the super attracting 4 cycle here, and the set B consists of the set A plus the extra critical value. And I'm going to insist that the extra critical value is not part of this super attracting 4 cycle. That is, I'm going to insist that the set B and A are different. B contains 1 more point than A. So, working with a map inside this class, by Adam's theorem, the deformation space is a 1-dimensional submanifold inside a 2-dimensional Teichmuller space, type B, and the target Teichmuller space is 1-dimensional. The notation pier 4, 0 star in this theorem means exactly that what I just said. Echo and I are working with rational maps inside pier 4, 0 where the critical points are not part of the same periodic cycle. A and B are different. So under these conditions, for any map F inside here, the deformation space has infinitely many connected components. So this is an example where the deformation space is not only disconnected, it's very disconnected. And I should mention that Tanya, Jeremy, and Nikita have a related result about this particular example as well. And then I just heard about some work of Mary Reese that also might be very relevant to this discussion. I'm not exactly sure how yet. Okay, so this is our theorem. I'm going to set this problem up. I'm going to turn it into a very explicit algebraic topology question, and then Echo's going to answer it. Okay, but to do that, I'm going to sort of reap some benefits of the context of this question. So just from the setting of the problem, there are a bunch of things that you can say, and sort of how you want to think about this problem, and how you might prove that the deformation space is disconnected. So I'm going to speak eventually after this slide about some general constructions and things you get for free just from the context of the problem. In order to do that, I'm going to need to know about the Modulite space. This, I think you saw in Nikita's mini course as well. Our Modulite space consists of all injective maps, sending our finite set A into the Riemann sphere, and those are up to post-composition by Möbius transformations. Our Modulite space is a complex manifold. It's isomorphic to the complement of finitely many hyperplanes inside this affine space here. And that's not so bad, not so hard to see. You take your set A and write it as little a1 up through little an. You can work with representatives of maps in Moduli space, of classes of maps in Moduli space. You can suppose that A map sends the first 3 points of your finite set A to 0, 1, and infinity, since we're working up to post-composition by Mobius transformations. And then the element of Modulite Space, represented by phi, is completely determined by this list of complex numbers here. And because these maps are required to be injective, all of these complex numbers must be distinct, and they cannot be equal to 0 or 1. Okay? So when I say M sub A is isomorphic to the complement of finitely many hyperplanes inside this affine space, you can see that using these coordinates. Okay, this is going to be very important for us. The Teichmuller space is the universal cover of the Modulite space. The universal covering map comes from mapping the class of the homeomorphism phi up here to its corresponding class down here. The group of deck transformations is the Teichmuller modular group, which I'll denote as mod sub A. And this is isomorphic to the pure mapping class group of the sphere marked with A. So I'm going to be talking a lot about this group of deck transformations, and I'll probably refer to them as mapping classes or deck transformations or automorphisms. Okay, so I mean elements of this group of deck transformations. So why is this space important? Why am I setting this up for what we want to do? Well, in general, I want to study a subset of a Teichmuller space, but working with the equalizer of 2 maps on a Teichmuller space is kind of a hard thing to understand. So what I want to do now is take a step away from this problem, away from the deformation space, define some things in general, and talk about when an equalizer of 2 maps between 2 Teichmuller spaces can be pushed down closer to Modulite space using quotients of the Teichmuller space of B. I want to push my maps kind of further down this tower so I can better understand the equalizer, the topology of the equalizer up here using some quotients. So I'm going to mention some things in general on this particular slide. So these are just generalities. So I'm going to start with a holomorphic map between these 2 Teichmuller spaces. That determines a subgroup, which I'll call G sub sigma. This is a subgroup of the group of deck transformations of this Teichmuller space over the Modulite space, and it's defined just in the following way. So it's a set of all G, so there exists a G prime in the Teichmuller modular group over here, so that for all points in the Teichmuller space, this is true. So all this is saying, of course, is that if you have 2 elements in the domain here, that any 2 elements that differ by this automorphism, then when you map those 2 points over here to the range, the 2 image points differ by a deck transformation or automorphism over here. That's all it's saying. So this is a very natural object to study, and in fact, in this particular context, you get a homomorphism whose domain is this group here, and that homomorphism just takes this G and returns G prime. So there's a companion homomorphism that you can define on a subgroup of the mapping class group or deck transformations over here. Let's remember that homomorphism. And then sort of for free, right from the definitions, this map sigma will descend to this quotient, the Teichmuller space of B, modulo this group G sub sigma. Just sort of immediately. Okay, so whenever we have a holomorphic map between these 2 Teichmuller spaces, we get this companion homomorphism, and we get a map defined like this, on this quotient, whose target is MA. Okay, any questions? So our context is a little bit different.
Obvious that G prime is unique defined by G.
Nope, but because the modular group acts freely over here, the homomorphism is well defined. Okay, that's a good question. So in our context, we have 2 maps from this Teichmuller space to this Teichmuller space. So we'll get 2 homomorphisms as they were defined on the previous slide. This is just generalities and definitions. These 2 maps have an equalizer, which I'll call curly D. Curly D is playing the role of the deformation space, which may be empty. So curly D is the equalizer on points, on elements of Teichmuller space of these two maps. A very natural object to look at now is the equalizer of these two homomorphisms. These two homomorphisms have a common domain, which is the intersection of their domains of definition. So we can look at all of those group elements, all those deck transformations in here, so that the homomorphisms are equal. So this is the equalizer of homomorphisms. And sort of, right, so I should say the deformation space could be empty, but I want to emphasize, even if it is empty, this group S for equalizer, S for this group S, still exists, okay? Even if D is empty. It's kind of interesting about what it actually is. We don't understand it very much. Okay. So as you might imagine, just sort of for free, this group S acts on this deformation space, acts on D. So let's suppose now that D is non-empty for the rest of this discussion. It will be in our particular example. And you get sort of this nice list of properties of this equalizer S, just from the context of the problem. So if you take an element with the intersection of these two common domains, the following are equivalent. That element is in the equalizer of these two homomorphisms if and only if it maps the deformation space to itself at least one point, if and only if it maps the whole deformation space to itself. So we'll give you an automorphism of the deformation space, or the equalizer. You get that for free just from the context of the problem. So what we're eventually going to do with our specific maps on the Teichmuller space and our equalizer in the context of our problem is, in order to study the topology of this space, which is what we're interested in, remember we're interested in whether or not this is connected, we're going to try to understand this group S and look at the quotient of the deformation space by this group S and study this, and then try to use this to understand that. Okay, so let me just say a few topological remarks that are going to help us with our topological prerequisites for our theorem. So here we are, we have this setup. This is the equalizer of those two homomorphisms. S is the equalizer of those induced homomorphisms. Sorry, D is the equalizer of the two maps on Teichmuller space. S is the equalizer of the induced homomorphisms that we have. Okay, so we're supposing D is non-empty, so we'll pick a base point. And I'll define D sub 0 to be the connected component of D containing the base point. And then I can define the subgroup E. E is for Echo and S is for Sarah. We're going to define the subgroup E, which consists of all elements of S that preserve the connected component containing the base point. Then it's clear that D is connected if and only if E is equal to S. And in fact, we can say more. If this quotient is connected, then there's a bijection between the connected components of D, its covering space here, and the cosets of E inside S. This is just algebraic topology. Okay? So what we're going to do to prove our theorem is, in our particular context, when we go back to what we're actually doing and work with one of those examples in the statement of our theorem, this space will be connected. What we're going to do is prove that E has infinite index in S, and then by this proposition, Adam's deformation space will have infinitely many components. That's how we get to our conclusion.
So you think what?
He asked if E, is there any reason to believe that E is normal in S? I don't think so.
These are those cosets, left cosets or what?
They're left cosets. Okay, get some conclusions back in our settings. So remember, we have two maps on Teichmuller space. We have the pullback map sigma F, the forgetful map sigma AB. Curly D is our deformation space, the equalizer, these two maps. We're going to get our induced homomorphisms. So this pullback map gives us an induced homomorphism, and I'm going to call its domain G sub F. It's a homomorphism from here to mod A. And if you know what the liftable mapping classes are, this subgroup contains the liftable mapping classes. The liftable mapping classes have finite index in mod B. So this is actually a finite index subgroup of the group of deck transformations of the Teichmuller space over the Modulite space. That's not so important. Okay, so we have one homomorphism coming from this map. We have another homomorphism here. I've called its domain GAB. Okay, coming from this map. This forgetful map here gives us the forgetful homomorphism on the level of mapping classes. The natural domain of definition for this homomorphism is in fact the entire modular group. And the homomorphism will take an element in here and just map it to its corresponding element in there. Okay, this is a forgetful map on the level of pure mapping classes. So this is kind of a complicated diagram, but I just put a lot of stuff in it just to keep everything straight. So here's our Teichmuller spaces, our red map sigma, our blue map, which is the forgetful map, the equalizer of these two maps. S is the equalizer of these two homomorphisms. We take this quotient here, or stick that inside here. G sub F is the domain here. Because the domain of this homomorphism is the entire group, G sub F is actually the common domain for both homomorphisms. So this quotient here, we get that the red map descends down to give you a map like this. The blue map actually also descends down to this level to give you a map like this. In fact, the blue map descends all the way down here. But I want to think of it as being defined up here. So now I have a quotient space that comes with a red map over to this space and a blue map over to this space. So I'm pushing the problem down this tower, and now I have a space, another space, and two maps in between them. The equalizer of those maps is now going to become important in this discussion. In fact, it sort of is an immediate consequence of the entire thing that D mod S will map to the equalizer. So this thing over here, it maps over here just by this composition, but the image of this thing in here will necessarily be contained in the equalizer of the blue map and the red map. And in fact, it maps in, this thing maps injectively in here. This is great for us because this quotient is a space that we can understand. We want to understand the topology of this thing, but I don't understand the topology of this thing. I don't know how to get my hands on it. I'd like to use this to understand that, but this is still kind of high up this tower. I don't understand this group S very well. But because this thing injects into here, and I understand this space, I can actually figure out what this is inside here as a topological space, work with it, and try to conclude something about this. And that's the strategy.
So you say that TB over GF is something that you understand?
Yes.
You mean so you understand this being more particularly radical zero?
In this particular context, for the context of our problem, if F is an element of pure 4-0, with A and B marked as we said, then TB mod GF is not pure 4-0. This is a two-dimensional space. But pure 4-0 will live inside of this two-dimensional space, namely as the equalizer of these two maps. And in fact, D mod S maps to pier 40 inside this space. So there's a way to think of it living in there.
I assume that that's pier 40 star.
It's pier 40 star, that's right. That's right.
Is it obvious that G sub n is greater than S?
Excuse me?
Is it obvious that G sub n is greater than S?
That G sub f is greater than S. Yes. The way that S was defined, it's defined as the equalizer of these two homomorphisms. So S will be a subgroup of the intersection of this natural domain of definition and this one as well.
No, but in your case, in example.
Oh, you're asking, do I know if it's different from G sub f? Yes, I do know it's different. More questions? All right, so I'm almost done, almost ready to hand it off to Echo. So for our particular map, we're going to be working with a rational function of degree 2. I'll tell you exactly which one in a second. We have a natural base point because we have a rational function. The base point in our deformation space is going to be the class containing the identity. And for our particular example, D mod S, the space here is connected. So remember, what we're trying to show, our base point up here in the deformation space lives in a connected component of D. The subgroup E was the stabilizer of that connected component inside the group S. Since D mod S is connected, the number of connected components of D is in natural bijection with the left cosets of E inside S. E is the stabilizer of the connected component containing the base point inside of S. So just for notation, the spaces that you're going to meet in a few moments, we're going to use curly W to denote this quotient here. That's this here. V is the image of D mod S inside curly W. And I'm going to give this red map a name, and these two blue maps are going to have names, just to transition over to Echo's slides. V, the image of D mod S, as Hubbard just asked, V, I said earlier, was contained in the equalizer of the red map and the blue map, but in our particular example, it is equal to the entire thing, and that equalizer is connected. That's how we know this is connected. So since we've chosen a base point, there are natural identifications of the groups of deck transformations in this picture with corresponding fundamental groups. Here they are. These are the natural images of the base point, which lives up here. S, this is actually kind of nice. S, remember what S was? It was the equalizer of the two homomorphisms, and we used it to get these quotients. In this particular context, it's going to be the equalizer of the induced maps on fundamental groups. So this map, red map UA, induces a map on pi1, from pi1 of W to pi1 of MA. And this blue composition here also induces a map on the level of fundamental group. So the subgroup of the fundamental group of W, which is the equalizer of these two induced maps, that turns out to be S. So we want to compare S and E, and we're going to compare those two things inside the fundamental group of W. So S is the equalizer here. What is E? Remember E, its definition, it was the stabilizer in S of a connected component of the deformation space containing the base point. E will naturally be the image of pi1 of V inside pi1 of W. V is the image of this thing inside here. You can look at its fundamental group inside the fundamental group of W. So our question of connectivity boils down to comparing the fundamental group of the equalizer of the red map and the blue composition inside the fundamental group of the big space with the subgroup of the fundamental group of W, which is the equalizer of the induced maps on the fundamental groups. So Kurt had a nice slogan for this. So the deformation space is connected if and only if S equals E. That is, if the equalizer of the maps on pi1 is equal to pi1 of the equalizer of the maps inside the big space, which is a nice way of formulating this. And as I've alluded to before in this talk, that is in fact not the case. What happens is this has infinite index in this, and Echo will tell you about that after this next slide. I'm almost done. Okay, so our particular example is this element of pure force 0. So here's a super attracting force cycle. Here's the map and a formula. The set A is this. The set B is this. It's the set A union the extra critical value. So you can do all these computations and compute that quotient space W. Okay. So W is naturally a space of rational functions mapping marked points upstairs to marked points downstairs. So an element of that quotient W consists of this data.
Now, is there any reason for you to choose that mysterious F when any old polynomial with a critical point, any quadratic polynomial with a critical point of period 4 would do just as well?
I like these coordinates. They're Jack's coordinates too in his paper. I think I decided I didn't like polynomials because you can't really use the fact that you have a polynomial because you're not marking the extra critical point. So you have a rational function of degree 2 with a critical value at infinity and then a super attracting force cycle over here. And actually, this is a better reason. When you choose your coordinates, you should choose them inside the set A and not inside the parts that are in B but not in A, because you want to remember the dynamical information in A. You want to work with Mobius conjugacy with maps respecting A, and if you normalize so things don't line up, then you're working in kind of a weird...
So was your answer yes or was it no?
It's no, I don't like polynomials.
You're not liking is one thing. And would it work? Would it in fact work?
It would work. It would work. It's just that everything would be a little bit skewed. It wouldn't line up the right.
Infinity would be a fixed point, right?
Well, you don't have to know that.
You can,
Infinity is in B, the dynamics on B is not visible in the deformation
I think
space.
it's just, for what I'm going to do for the coordinates, it's going to matter that we want to fix 0, 1, infinity, and then have an extra coordinate. That's another reason why it's
I think the math will go through. It's just much more convenient to do this, and I don't know why you would do anything else. You want to normalize so
Because I
that
don't know that map at all. And I know the polynomials.
the map itself isn't very important. The reason I'm giving you a specific one is to just be careful and choose an actual base point. And I want to choose a real base point. Okay, so anyway, this quotient space W that we'll work with, it's a space of rational functions that map this set of marked points upstairs to this set downstairs. The rational function depends only on X and Y, so you can identify this with this, X and Y, this point and this point give you coordinates on the quotient W. This extra critical value Z is just a function of X and Y. And then in these particular spaces, here is our W space, maps over here to MB, that maps over here to MA. This point of W maps over here to MA. And you can see that the equalizer on points of the red map and the blue composition, that's exactly when X is equal to Y. And over here, when X is equal to Y, you get a rational function that has a super attracting cycle of period 4. Okay. So the image of the deformation space is the equalizer, is inside W is the equalizer of these two maps. And now I really have to hand it over to Echo. Take it away.
Thanks, Sarah, for setting this up. No, I think it's one of the faster. But so thanks for letting me butt in like this. It's really an honor to speak, especially at a complex dynamic systems conference. I think it's interesting. Okay, so just to review a little. Sorry, but I need my notation. So F again is in pure 4 0 star. Def, which we're trying to prove that def is W that's given by modding out TV by the subgroup of the mapping class group, which is consists of the equivalences of F with other rational maps. And S is the ones that are equivalences with combinatorial equivalences with F. And when we mod def out by that, by S, we get a space V. And that's going to sit inside W. That's not completely obvious, but it turns out that it sits inside W in our example, and V is connected. And what we want to know is, in order to show that def has infinitely many components, we want to show that the stabilizer of a connected component of this is not equal to all of S. In fact, it's infinite index. So if we can show that, then we can show that there are infinitely many components in def. So that's what I'm about to do. So we have these groups, these subgroups of mapping class group. So L is the fundamental group of W. It's the equivalences of F to other rational maps, to possibly other rational maps. S is the one which is equivalences with F, and E is the one which comes from the fundamental group of def. V. So it acts on it's the stabilizer of a connected component of def. But here's another way to sort of picture it very quickly. So all these things, the mapping class group, you take a point, take a base point. We can take the base point corresponding to F and act on it by elements of the mapping class group in TV. And just for fun, let's make a path joining the two things. It's a simply connected space. It doesn't really add anything at this point. Then we have two maps, sigma F, the pullback map, and the sort of inclusion map, the forgetful map. And the forgetful map, let's say we draw it like this, so this path becomes this path. This red point is the image of that point under the forgetful map. And then the blue one is the image of this red point under sigma F, the pullback. So in general, there's not, you can't really say much about where these lie. Def is when these two map to the same point. So you know that this point is in def if these two things map to the same point. Now, so that's the general case for the what's called the liftables or the fundamental group of that W space. If you're in that space, then this here again is the same, just include forgetful map. This one will now map to something which differs from the image of the forgetful map by a mapping class group in the module in the rel A, for the moduli space of the points A and P1. So this just lies on a fiber above the moduli space, is what I'm trying to say. So that's the space L. Now inside that is S. S is the thing that we want to show is large compared to E. And so what does that look like? Well, S has a property that sigma F and sigma AB will map this red thing to the same point. Because this red thing is going to be in depth. Basically what you can think of is that it's another point in depth. G takes the base point to another point in depth. And then this path is, again, just any path. It's going to map to, by sigma AB, by one path, by the pullback map to another path. They don't have to be the same path. Now, of course, TA, this is all happening in TA, is simply connected. So these are isotopic, of course. But there's no reason to think that you could choose G so that these paths are actually equal. Okay, so what is E? E is exact. So now think of this green thing as being a component of depth. And suppose you could push G, this path, onto depth. In other words, this base point and this other point are in the same component of depth. So same thing, right? So then this path is in depth. That means that that when you map by these two maps, you get exactly the same path. Okay, so this is a sort of visual picture of what computation. So this part, this is the, so we reduced to an algebraic topology problem. So first we need coordinates. We're going to make a space. We're going to compute fundamental groups and show that one group has index infinity and another group. Okay, so as Sarah showed, you can sort of choose, make 0, 1, infinity x be your set A, 0, 1, infinity y, z, say be your set B, and just build up the combinatorics. Now F is when x and y are equal, and has these combinatorics. But in general, W, which is the space of all rational maps which have the same sort of combinatorics and combinatorially equal, but not necessarily giving you the rational map that you started with. So x and y can be different things, and then z is just the image, is just a critical value. So that gives you coordinates in W, and it turns out because of the way because of this particular example, it's not always true. W actually embeds, because of this triangle here, into MA cross MA. So, and you can see this also just by looking at the coordinates. So, you have W is really x, y, and the rational map, but x and y determine the rational map, and they determine the point z, which was the critical value. So z is a function of x and y. And so if you map xy to xz, its image in MB, remember, right, we're looking at y and z here. So sorry, that should be a y, yeah, yz. So xy maps to yz goes to y, and then because we're forgetting the z, and xy goes to x is this map. So this says exactly what the maps are in terms of the coordinates. So now let's make a picture of this. So MA is just P1 minus 0, 1, infinity, which is just C2 minus 0, 1. So MA cross MA is just C2 minus 2 vertical lines and 2 horizontal lines. Okay, so this is a 4-dimensional space. These are one complex dimensional lines. They intersect in these 4 points. So from what I'm going to do now, we're going to start having to really think about 2-dimensional planes inside 4-dimensional space. So just to start getting used to that. And then we have projections onto the different components MA. This one is mapping straight to MA by the basically the forgetful map, and the other one is by the pullback map, the pullback map and the projection. Okay, so what's W? W is embed inside MA cross MA, and it's a Zariski dense set, so it's just a complement of a few more curves, a bunch of more curves. And these can be computed directly because we have a specific map on. So given whatever rational map you start with, here for 0 star, you get these curves. And so W is C2 minus that original L, the red lines, union a bunch of curves. And then V, which is the image of depth, is the equalizer, is going to be exactly the diagonal intercepting with W. Okay, what you'd think it would be. So what is that just saying? That's saying that the forgetful map and the pullback map are equal, which is what the definition of depth is. Okay, is any, please interrupt me if I'm not being clear. Okay, so what is S? Although, again, there's so many different ways of saying what each of these groups mean. For our purposes, I don't know if you can see that, it's kind of faint, but we can characterize as follows, as a subgroup of the fundamental group of W. Okay, remember L is sort of this L here, not these L's, sorry. This L is the fundamental group of W, the complement of these curves, and S is going to be some subgroup of W of L. And so how do we know when an element is in S? So gamma is in L if exactly when the image under this projection and the image under this projection are homotopic. So what we can do is, okay, just concentrate on one projection and see what it is, lift it up to L2, and then project the other way. And so you can basically, any element of gamma L, we can write as sigma is psi eta, where psi is in the image of, let's say, the vertical line, and eta is in the image of the fundamental group of the horizontal line. And then to be in S, you just have to have that the projection of eta, which is 0 in one direction, is exactly the same as the opposite direction for C. Does everybody see that? So basically, you have a loop on L1 and a loop on L2. So this loop on L2 maps to the identity over here, and this loop on L1 maps to the identity over here. And what you need is that the product, gamma, maps to the same thing by P1 and by P2. But since P1 of gamma is P1 of eta times C times eta, which is P1 of C times P1 of eta, P1 of C is 1, so you just get this left over. And same with this. Okay, so this is the condition you need to be in S. And from that, you can see that S is not a normal subgroup of L. You take your elements of S, you write them as something vertical and something horizontal. Then if you conjugate only the vertical part by another vertical element, you'll change the one side and not the other. You'll go outside of S by conjugation. Okay, so now we simplify W. So W, remember, had all these curves in it, which are sort of blurry here. But the really important thing is, I don't know why these aren't meant to be so faint, but you have the original red lines. There's this nice vertical. If you only had the red lines, then the fundamental group would be abelian. So that's not enough information. But if you also add in this green line, which was part of the original curve set, part of the curves, then you get a fundamental group which is not abelian. And the fundamental group of W surjects onto the fundamental group of W hat, this simpler group. So pi1 of W, W includes into W hat. The pi1 of W surjects onto pi1 of W hat. And then we keep simplifying our space W. So we have W hat, which is, I'm so sorry about these pictures. Maybe I should try to draw it, because it's really easy to draw, actually. So we have this more complicated space, but this doesn't come out in color, does it? Okay, let's just go back to this thing. Okay. So we take W, we put it inside W hat, and now what I'm going to do is this W hat, the way it's chosen, it's a tic-tac-toe thing with this green line. So there's a symmetry across V, actually, right? So we just mod out by that involution, by that reflection, and we get W bar, which has one image for the two lines y equals 0, y equals 1, x equals 1, and another line for y equals 0, x equals 0. The green line just goes to the green line, and then V hat maps homeomorphically to V bar here. And this map is just a map that says xy to x times y, comma x plus y. It's something this is, W bar is the complement of these two red lines and this green one. So, so this, in particular, this 0.10 is not in there. So we can blow it up and get this exceptional curve. And the complement is still the same. And then we can project onto that exceptional curve, which is just a P1 minus these 3 points, so P1 minus 0, 1, infinity. And so we have, and then what do we get? We have a bunch of projections from pi1 of W to pi1 of this thing to pi1 of W bar to pi1 of C minus 0, 1. So we've very much simplified our groups. Now we have these two subgroups, E and S, that we're comparing. Now E is the fundamental group of V, and V is just going along, not changing under these maps. And S was, you can get by taking something in L1 and something in L2, and with the same projections, right? So you're multiplying them together. So what happens there is when you do this map, it just goes to a square of something that lies on this dotted line. This dotted line goes to, so this dotted line here, and which maps, straight down, 1 to 1 onto C minus 0, 1. Okay, so, right, so what we have is these are surjective maps. These are homeomorphisms on V, and this V to this line is a degree 2 covering map outside the omitted loci, and so the fundamental group of V is injective into here, and the fundamental group of this is a free group. Okay, so putting that together, we can find an infinite set of cosets very explicitly. Okay, we're going to find an element of S all of whose powers do not lie in E. That means if you look at the cosets, so it's going to be called gamma. If you look at gamma times E, or gamma to the n times E, and gamma to the m times E, they're the same coset if and only if gamma to the m minus n, it lies inside E. But if no power of E, the gamma is in E, then of course that's not going to happen. So you get an infinite number of cosets, which means E has infinite index in S. Okay, so I just need to find a special element. So you probably now can do it yourself, but basically, so this is just a fun exercise. So you just take something in pi1 of L1 that's not trivial in here, or in pi1 of W, which you can easily do because remember pi1 W has tons of other curves. You can always wind around curves and things like that to make something non-trivial, but still come from pi1 of L1. Then take its sort of reflection in pi1 of L2, map it over to here, etc. And all you want to do is find something like that so that this projection here is trivial. Okay, so that's what I'm going to do here. So that's what I'm saying here. You make gamma, which is this product form, so that when you go all the way down to here, you get something trivial. If you do that, you're in S. You're not in V because V injects into here. Right? The fundamental group of V injects into this free group. And so if it's a non-trivial element, it can't come from V. Okay, so that means that well, this is the last slide. So that's an element whose none of its powers is in E for all n, and so these give you distinct cosets. So that is the entire group. And just thank you very much.
So thanks Heiko and Sarah for this great talk. I guess we have time for some very quick question, I guess.
So do you have any interpretation of the various components?
No. That's a great question. And one thing that's great about this project is that it seems to have raised many more questions
same as the, when you forget the points outside of A downstairs in B. So you're moving points B around. Inside the points B, you have A sitting there. Then you lift by rational maps, so you want to lift to a covering and then lift the complex structure. That puts A in a particular place, and you want that A to be the same as this A. So you can think of the connected components as exactly where you can really push the points in B around so that A doesn't move. And so that's how you can be in B. So when you think about it like that, it seems amazing that the deformation space is so big. But
Yeah, it's not connected.
but it's not connected because you have these other kinds of things that can happen. So as I was saying about the way you can describe gamma, the thing that's not in E. So the gamma comes from doing a vertical loop and then doing a horizontal loop. That's the same as doing a move on the base that doesn't change A upstairs. And then doing a thing on the base which is a point push of the extra points that doesn't change A upstairs. And if you do that, that's not in, so it's not fixing A because you're changing A. But when you change A, you're not changing A downstairs. And somehow putting that together gives you something in def. So def, def is kind of I don't know, to me it's a little bit hard to understand. That's, I think, the harder question than understanding the connected components. At least it's for me intuitive.